Okay, so we'll cover chapters 22 and 23 today in this lecture. So pretty much we're doing everything we just did with proportions with means instead. So we're using the central limit theorem just like we did before. Remember with the central limit theorem, the standard deviation of all possible samples of size n, because all sample means are normally distributed with mean mu and standard deviation sigma over square root of n. So if we know what the distribution of all samples looks like, and we have a particular sample, we can estimate how far away the true population proportion or population mean should be from that. Problem is, most of the time we won't know sigma. That's about the whole population. Remember, we're trying to estimate mu here, and if we don't know mu, there's probably no way we're going to know sigma. So when we were doing proportions, we had this good estimate. We did the standard error as square root of p hat q hat over n. So we could try something like that here. We could try the standard error of all the x bars. We call them x bars. Your book calls it y bar. Is s over square root of n. We could try that, but it turns out it doesn't work very well for small samples. And this guy right here, Gossett, let me show you his picture. This guy here figured that out. He worked for the Guinness Beer Company as a mathematician doing statistics. And his job was to take samples of beer, and if the sample was bad, then they'd throw out a whole batch, that kind of thing. And he noticed they were throwing away way too many batches of beer. And that's because they were using a normal model. And he realized that when your sample size is small, using your standard error or using your sample standard deviation as a fill-in for sigma just doesn't work. So he went through a whole bunch of work and developed a brand new kind of statistics called t-statistics. And he took it to his bosses at Guinness, and they said, great, that's awesome. Don't tell anybody about it. And he said, but this is brand new mathematics I've invented. I could change the world with this. And they're like, no, if you tell everybody about this, our competitors will use it. Other beer companies will use this. So he was forced to, eventually they said, okay, look, you can publish your results, but you're not allowed to use your name because everybody knows you work for us. So he had to publish his results using the pseudonym A Student. And because of that, this branch of mathematics is known as students' t-test or t-statistics. And this poor guy didn't get the credit he deserves. So I want you to see his picture and know his name. This should be called Gossett's t-statistics. All right, so here's our setup. We're doing confidence intervals for means. We're trying to make predictions about mu, the population mean. So first we have a few conditions we're supposed to check. We got to make sure we take good samples, of course. The samples need to be independent. Our population should be nearly normal. And I put that in quotes because this depends on your sample size. For really large samples, like if your sample size is bigger than 100, you really don't have to worry about this at all. But if your sample size is really small, say less than 20, then your population really needs to be a normal distribution for this to work. And of course, just like with proportions, our sample size can't be too big. It can't be bigger than 10% of the population size. So we have our sample, the sample mean, and S. And N, of course, is sample size. Okay. Now, we're not going to do any of these by hand, but I'm going to show you, just so you have the background knowledge, how you would do this by hand. So we're trying to estimate mu, the population mean. We got to find our margin of error. So before, remember we did Z star and we had all those different Z stars. We had a whole list of them, like for 95%. So recall, this was a long time ago. At 95%, our Z star was 1.96. Well, when we're doing means, we don't use Z's, we use T's because of this work that Gossett came up with. And T's depend on which or what your sample size is. Let me show you this table at the back of your book. So that was our Z table. In the back of the book, we also have this T table. And that depends on your sample size. So if we wanted to do a 95% confidence interval, this is the way we had to do it when I took this class. We would come to this table and we would find the appropriate T star from this list depending on our sample size. Where DF here, degrees of freedom, is N-1. So if our sample size were 18, what would DF be? 17. So we would come down to 17. We're at 95%. I think that was this column. This is what we would use for our T star. What if our sample size were 137? What would our degrees of freedom be? 136. So let's scroll down to 130. Oh, it's missing. There's no 136 in here. Oh, well, I guess I can't give you that problem. That's the way it works when you got to do this by hand. When you're writing the questions, you got to make sure the number you're giving the students is in the list. So that would limit me. Or I would have to tell you guys to go out and find a better T table. But notice what happens here as N gets bigger. Look at these T stars. They're getting closer and closer to 1.96. The same thing we used with Z's. As N gets bigger, T's look a lot more like Z's. So they used to tell us when I took this class, if N is bigger than 50, forget about all this T crap, just use Z. Just forget about using one of these numbers here, just use 1.96, whatever, it's close enough. Okay. We're not gonna do any of that. I'm gonna show you how to do all this on the calculator. But what you would do, so if you were doing this by hand, you would go to that table there, look up T degrees of freedom, where your degrees of freedom is N-1. Find the appropriate T star, multiply that by the standard error, which is S over square root of N, and that would give you your margin of error. And then your confidence interval would be your sample plus or minus the margin of error. And you would say we are blank % confident that the thing we're looking for is between those two numbers. But we're going to do everything on the calculator. Okay, so let's do an actual example here. All right, so here's our setup. We do a sample of 120 Valencia students. We find that their average GPA, I just made up numbers here, don't quote me on this, is 2.81 with this standard deviation. We want to find a 95% confidence interval. Okay, so the first thing we do every time is identify our variable. Let mu represent, what is it we're studying here? Let mu represent the mean GPA. You have to say the word mean. Everything is means now. Then our sample, X bar, S, and N, they'll always give us all three of these every time. Our sample mean was 2.81. Sample standard deviation was 0.63, and N was what, 120? And now we use the calculator. Okay, so just like before, we're going to go into stat and over to tests. And now the only buttons we're going to use are 2, 4, 8, and 0. for the rest of the semester until the final, 2, 4, 8, and 0. Are we doing a test or an interval here? It was an interval. All right. So you like button 2? Does that say interval? No. What about 4? No. Okay. 8? 8 says interval, and so does 0. How many different samples did I have? 1. I only had 1 sample. So this button, like let's click in there. Look at all that stuff it's asking for. I didn't write all that down. That's the wrong one. I want button 8, T interval. Everything will say T from now on. Sometimes they're going to give us all the data. I did a video where they gave us the data, where they'll give us 50 different data points, and we have to type them all in. Here they gave us the stats, so I make sure stats is highlighted. And now I just type in, literally type in my 3 numbers and hit enter. That's it, 2.81, oops, 0.63, and 120. It was 95% confidence. I hit calculate, and I'm done. So this is my confidence interval, and I just write out the answer. Remember, we're predicting this, mu. There's no success or failure here. There are no percentages. Nothing here is a percentage. We're talking averages here. So then we would say we are 95% confident that the mean, you have to say the word mean or average, the mean GPA is between those 2 numbers. And if we had units, we would include units. GPA doesn't really have units. But if those were in inches or whatever, we would say inches. And that's it. That right there is a confidence interval. That's the entire process. Okay, what about hypothesis testing? So hypothesis testing for means, it's going to be the same idea we did before. Now they're going to give us a sample, an X bar, an S, and an N. First thing we're going to write out is let mu be the mean, the population mean. And then our hypotheses, instead of P's, we're not talking about proportions, we'll have mu's. So our null hypothesis every single time, always, will be mu equals some mu naught. And then our alternative will be no, mu is less than that, or it's greater than that, or maybe it's just different, and we don't care if it went up or down. We're going to draw our picture every time. So right in the middle, we'll have what we believed the average was before we did the sample. And then say, for example, our sample is higher than we expected. So maybe our sample mean will be up here, and we would shade above, and that would correspond with mu greater than mu naught. As our alternative, we get our p-value. If the p-value is less than alpha, we reject the null and accept the alternative. If it's greater than alpha, we fail to reject. Exactly the same stuff we did before, just now instead of saying proportion over and over again, we say mean over and over again. No success or failure. We don't have P's anywhere or Q's. We have mu's and X bars everywhere. Okay, what about the 2 sample stuff? Okay, so if we were doing a 2 sample confidence interval, then we'll have 2 groups. We'll have group 1 and group 2. Each group comes with their own sample statistics. A little out of focus there. So we'll have our two groups. We will always choose group one to have the higher sample mean, always. You get to choose who's one and two. Choose group one to have the higher sample average. Then our confidence interval, don't forget this step. Make sure you always write out, let mu be blah, blah, blah. Don't mention the groups here. I just graded your group quizzes. And that second one, the one about Britons versus Canadians, who reads the most. You guys, a lot of you here, when you said let P be, you've mentioned the groups here. If in defining your variable, you mention your groups, you've misunderstood what your population is. Your population is everybody combined. So if our groups are men and women, our population would just be people. It would be let mu be the mean that people get. And then we type all this in the calculator. This would be the button that says two sample interval. If I had to guess, I would think that's button 0. We could check in a minute, but I think that's button 0. We get some interval, low and high. And then that's a prediction of how much higher group 1 is than group 2. So our sentence will always be, we are blank % confident that the mean for group 1, we're talking about means here, is between the first number, not percentages. These are not percentages. These might be miles per gallon or something. Higher than the mean for 2. Okay, and I do videos on all of these. I do a whole bunch of examples. And then finally, hypothesis testing for 2 groups. Our 2 sample tests. Same idea, we're going to have group 1 and group 2. We get an X bar 1 and S1 and N1. Oh, it should just be N. Same idea, choose group 1 to have the higher sample mean. So you get to pick that. Choose. And then our hypotheses, remember, you have to always write out your hypotheses. Your null hypothesis will be that those 2 have the same average. The difference between them is 0, which means that's the same thing. If you like writing it like this, that's perfectly fine. On average, the groups are the same. And then the alternative, if you choose things properly, if you choose the proper group 1, then your alternative 99% of the time is going to be that, which says on average group 1 is higher than group 2. And then just like with all hypothesis tests, you get your p-value, less than alpha, reject, greater than alpha, fail to reject, and all that. So it's the same stuff we've been doing all through the test 3 stuff, only now our symbols changed a little bit.